Hello and welcome back. So we have started our second playlist. We are covering International Edexcel A-level syllabus. And last time we covered momentum and impulse. And this is the second chapter of Unit 4 for the mechanics. And we are starting second chapter, that is circular motion. So first we'll cover some basic concepts and then I'll show you how you can use these concepts to solve these problems. So the first thing is you have to understand the definition of radians. Radian is another unit of angle. For example, just like we measure angle in degrees, in physics, we measure angle in radians. Radians is defined as the ratio of arc length divided by radius of the same circle. So imagine that you have an object moving in a circular orbit, and this is, let's say, radius of the orbit or a radius of the circle. This is center of the circle, sorry, and this is radius of the circle. So what is arc length? This distance here, this curved path, this is what we call arc length. So arc length. And if you divide this arc length by the radius of the same circle, then you get this angle, and this will be in radians. Now, when will you get 1 radian? 1 radian will be when the arc length and the radius are equal to each other, right? Because you're taking the ratio. So if the numerator and the denominator, they are the same, you will get 1 radian. So 1 radian is when arc length and the radius are exactly equal in magnitude. What about 360 degrees? If this thing goes around in a complete circle, so what will be, how many radians will we have? It's very simple. If it goes in a complete circle, first you have to answer what will be arc length. In other words, what will be this red distance? So if it goes around a complete circle, this red distance will be complete circumference of the circle, which is 2 pi r. So we can write that for 360 degrees, or for one complete rotation, we have theta, which is equal to s over r, but s for 360 degrees is 2 pi r, which is complete circumference, divided by r. So you see r's get cancelled and you get theta equals 2 pi radians for 360 degrees. This is an important relation we want to remember, that one revolution or 360 degrees equals 2 pi radians. You will see we will use this relation to solve many problems and to convert units. Next, we want to understand what is angular displacement. Angular displacement is exactly this theta that we just discussed, radians. So as something moves in a circle, you can either measure arc length, how much distance it covers, or another thing that you can do is you can measure this angle instead of measuring this arc length. So for example, if this object goes from, let's say, from here all the way to here, then this is, let's say, the center of the circle. So instead of measuring this length, this d, what you can measure is this angle. And you can say that the angular displacement of this object, let me draw the object in red color. So this object covered this distance. So you can say that the angular displacement of this object is pi radians, right? It will be pi because this is not a full circle. This is half a circle, and we know that in one complete circle we have 2 pi radians. So in half circle we'll have pi radians, right? So this is angular displacement. How is angular displacement related to linear displacement s? You can just look at the equation of radians. Angular displacement is s divided by r. So linear displacement s will be r times angular displacement. And this again is a very useful equation to remember, that linear displacement s equals r times angular displacement. And this is important to remember because this same pattern will repeat for each angular and linear variable. The relation between linear and angular variable will exactly be like this one. Next, what is angular velocity? So just like linear velocity, remember that linear velocity is linear displacement over time. So angular velocity will be exactly like this definition. It will be angular displacement over time. What is angular displacement? Angular displacement is theta. So it will be change in theta over time. And this is angular velocity. Okay. So the definitions are exactly the same. Linear velocity is linear displacement divided by time. Angular velocity is angular displacement divided by time. And you can also write a relation between linear and angular velocity. And again, the relation is that v is the linear velocity. It equals r times omega. You see, this relation is exactly the same as this one, s equals r theta. So again, we have linear variable equals r times angular variable. And third one is angular acceleration. Just like, again, how do we define linear acceleration? We say that linear acceleration is change of linear velocity over time. So angular acceleration, we represent it by alpha, will be change in angular velocity over time. And again, what is the relation between angular acceleration and linear acceleration? If you guessed it right, then you are following what I'm trying to explain, this pattern, that linear acceleration will be r times angular acceleration. So if you understand these three, then almost you can solve, I can say 30-40% of the questions. But if you also understand these two, then you will be able to solve 100% of the questions from this chapter. So what is centripetal acceleration? Centripetal acceleration is acceleration of anything that is moving in a circular orbit. So anything moving in a circle, it will always have centripetal acceleration pointing towards the center of the circle. Okay, centripetal acceleration at any point is the direction of centripetal acceleration is towards the center of this circle. So this is AC. Now, what is the equation for AC? Centripetal acceleration is just given by v square divided by r. For now, you just remember this equation because there is a question in which you have to prove this relation. So I will derive this equation in that question. For now, just understand that it's v square over r. And now you can write it in different ways, because if centripetal acceleration is v square over r and v is r omega, so we can substitute v here. So it will become, since it's v square and v equals r omega, we'll have r square omega square divided by r. So what I did, I substituted this v equals r omega here, and I applied the square. So the square will act on r and omega, r square omega square. The r's, one of the r's will cancel, and you'll get AC equals r omega square. So here what we did, we eliminated v and got AC in terms of r and omega square. What we can do, we can also eliminate this r and get centripetal acceleration in terms of v, which is linear velocity, and omega, which is angular velocity. So how can we do that? We can rearrange this equation for radius. So using this equation, we have that radius equals v divided by omega. And now this time what I will do, I will put this radius in this equation here, right? So what will I get? I'll get that AC equals v square divided by r, but r is v divided by omega. So I'll write v over omega. And now you can see that this v will cancel with this v, and you'll get that AC is just equal to v times omega. This is very unique, and it looks kind of wrong, this equation, but it is a useful equation. This one and also this one, AC equals r omega square and AC equals v square over r. So again, you don't have to memorize each of these equations separately. If you understand the basic definitions of radians, angular velocity, angular acceleration, and you understand that AC is v square over r, then you can derive this one and this one. Finally, we have centripetal force. Just like any force, centripetal force must also be equal to ma. But since it is centripetal force, the acceleration that we will have will also be centripetal acceleration. So you can substitute centripetal acceleration here, and you will get that Fc equals mass times, for AC, I will write v square over r. So it's v square over r. Mv square over r is centripetal force. But again, you can also write AC in terms of r and omega. So if I substitute r and omega square for AC in the equation for force, I'll get m r omega square. So this is another equation for centripetal force. This is one equation. The most standard one is the first one, but sometimes you have to use this one. And finally, we just have one more equation to understand, and that is the equation of time period. So how do we define time period for a circular motion? It is the time for something to complete one rotation. And we can derive the equation very easily. We will use the equation of speed. Speed is total distance divided by total time. So total distance, if something completes one rotation, will be the circumference of the circle. So 2 pi r divided by total time, I'll write capital T. If I rearrange this equation for time, I will get time equals 2 pi r divided by v. Now this is also equation for time period, but we want to write it in terms of this omega. So you see we have relation of v, r, and omega. I can use this to replace this r over v by omega. You can pause the video, do it yourself, see if you can do some simple algebra. I will do it here. V equals r omega. If I want to find r divided by v, I need to divide both sides by v, and I need to divide both sides by omega. So in the end, I will have 1 over omega on the left side, and on the right side, I'll have r divided by v. It means this r divided by v, I can replace by 1 over omega, and my equation for time period will be 2 pi divided by omega. I can also rearrange this equation for omega. Omega will be 2 pi divided by time period. And finally, if I use one more relation, that is time period and frequency. So linear frequency and time period are inversely related. Time period equals 1 over frequency, or frequency equals 1 divided by time period. I can use it here to write omega equals 2 pi divided by, sorry, this is 1 over t, so it will be 2 pi multiplied by frequency. These three equations are so important, and they are used in almost every other problem from circular motion. So it's really important that you can derive these equations, or you have these equations on your fingertips. You can use it without looking at the equation sheet, and then you will be able to solve these problems. If you cannot write these equations without looking at the equation sheet, it means you haven't solved enough questions, you haven't done enough practice, because after, even if you just solve 10 questions on time period and angular motion, then you can write these equations without looking at the equation sheet. Okay, now I hope everyone is on the same page and we can start solving these questions. So the first question, we are given that the toy aeroplane completes 12 revolutions in 6 seconds, right? So what is this thing? Revolutions per second. This is kind of rotations per second, and rotations, we know that we measure rotations in angles, right? So it is radians per second somehow. So this is actually omega, but the units are different. It is revolutions per second. We need omega in radians per second. So that is the question. Actually, you have to find omega in radians per second. So this is not a question, this is just a unit conversion problem. So you are given that omega equals 12 revolutions per second, and they want you to find angular velocity omega in radians per second. Now I have explained how to convert units multiple times, but again, I will use the standard method. What we do is we will multiply any unit with a conversion factor. I always tell my students to use conversion factors. Don't try to memorize this like it's divided by 2 pi or it's divided by 1 pi, something like this. Because under pressure in exam, there is a big chance that you will multiply when you were supposed to divide. So always use conversion factor so that you can see what is happening. So what we do, we want to change revolutions into radians. So our conversion factor will be a conversion factor between revolution and radian. We know that 1 revolution equals 2 pi radians. It means that if I divide 1 revolution by 2 pi, now these two things are equal. So if you divide equal things, you get 1. And in math, you can multiply anything with 1, right? It's a valid operation. So I can multiply this factor here, but you see, I want to cancel revolutions, right? So if I use this factor, it will not cancel the revolution because revolution is here. And if I write revolution here, they will multiply, they will not cancel. So I will invert this conversion factor. Now I will use 2 pi radians divided by 1 revolution. And now you see how easily revolutions cancel with revolutions. 2 pi will get multiplied with 12, and you will get your final units of radians per seconds. But I just realized that I haven't written, this is 12 revolutions in not 1 second, it's 12 revolution per 6 seconds, right? So conversion will be 12 times 2 pi divided by 6, which is option B, 12 times 2 pi over 6. Now the second question is very important to understand because I specifically searched for this problem. so that I can show you how to solve these type of questions. And you should be able to like identify similar types of questions, okay? So for example, this question, and I'll show you another question. I have it here, I think. Yes, this one. And I'll see if you can figure out the similarity. So the question is that the car is going over a bridge, and this part is part of a circle, right? You can imagine that this is like a big circle. And the question is, which of the following expressions give the force from the bridge on the moving car? Now we know that any contact force is normal force. So actually they are asking us to find the normal force. So for any question like this, what you do is you write an equation for net force, okay? And net force or any circular motion or part of a circular motion must be equal to centripetal force, which is mv square over r. I'll write it in 2 steps. So any net force, if anything is going in a circle, must be equal to centripetal force, which is equal to mv square over r. Now, we also know that net force is just sum of all the forces acting on an object. So we know that this car has weight acting on it, which is downwards, mg, and it has normal force acting upwards, right? And we also know that centripetal force should always point towards the center of the circle. Now, if the net force of the net result of these two forces is pointing towards the center, it means that mg must be greater than normal force, right? So I have to write mg first so that I get the right sign, which is towards the center. So mg minus normal must be equal to Fc, which is the centripetal force, which is mv square over r. So I hope you understand this, that how do you determine which one to call positive and which one to call negative. Some students, what they do is they say that up is always positive and down is always negative. So if you follow this thing, you will get a wrong sign here, because normal will be plus and mg will be minus because it's pointing down. But this is not how you write these signs, okay? You have to think logically, and it depends on the question which direction should be positive and which direction should be negative. So always think about this. In which direction do you want your net force to be? If the net force is pointing down, it's better to call the downward force positive and the upward force negative, so that you get a net force in the downward direction. So that's it. This is our equation. And now they are asking for net force, so we can rearrange this equation for net force. And you can see that net force will be equal to mg plus not plus, sorry, it will be minus mv square over r. So what I did, I moved this n to this side, it became plus, and I moved this to this side, and that's why it's minus mv square over r. Mg stays exactly where it is. So this is option C, mg minus mv square over r. Now I will skip this question because I want you to solve this one, because these two questions are similar. So what we have here is a bucket, 8 kilogram is actually, this is filled with water and attached to a string of length. Again, there is some space of 0.5 meters. What is the minimum speed the bucket must have at the top of the circle? Again, another typo, so that no water spills out. So let's first imagine what is happening. We have a bucket which we have tied to a string or something, and we are rotating it, and the bucket, add drawing, I can draw a bucket like upside down. So this is the handle of the bucket, and here we have some water in the bucket, right? And we are rotating it in a circle. Now the question is asking that the mass of the water is this, or mass of the bucket is this. What must be the minimum speed so that the bucket, so that no water spills out? So first, let's see what are the forces. We have force of tension in the string acting downwards, and we have another force, I'll draw it in different color, which is weight. So at the top, both the forces are pointing downwards, right? And we know that centripetal force should also be downwards. So we can say that net force must be equal to centripetal force, which is equal to mv square over r, And for net force, we just count the number of forces. We have only two forces, both of them pointing downwards. So we can write that tension plus mg must be equal to mv square over r. Now, the first part of the problem was to write this equation in the right form and with the right signs, right? So this is done. The second part of the problem is to find V minimum, the minimum speed the bucket must have at the top, so no water spills out. So if velocity is minimum at the top, what will happen? The tension in the string will just be enough so that it is at the top, which means the string will not go slack, like it will not be loose so that the bucket like falls straight down, but there will also be no pull on the string, right? So for V minimum, the tension at the top, remember, will be zero, not at the bottom, okay? It will be some different force at the bottom because tension and weight will be pointing in opposite directions. So it will be different story if the bucket is down. So I've seen a lot of problems like this when they ask something about when something is at the top of the circle, or is it or when it is at the bottom of the circle. So these vertical circular motion problems, you need to be very careful with these problems. And that's what I was saying, that you should be able to recognize a problem type just by reading the statement. So whenever you see something vertical motion problem, this is problem, you should solve it like this. Remember, you will always use net force equal to mv square over r, or net force equals centripetal force. And then depending whether the object is at the top of the circle, at the bottom of the circle, or at the like this, in this case, although it is at the top, but there is no string attached, so there is normal force, right? So these are all the types of problems that you can expect. There will be some string and you will have a vertical circular problem, vertical circular motion problem. And it will have two types. The object will be either at the top of the circle or it will be at the bottom of the circle. This equation will look different depending on the position. And let me also write, if it is, for example, at the bottom of the circle, how will the equation look like? So we'll have weight acting downwards and tension acting upwards. And we know that since it's circular motion, the net force we need is towards the center of the circle. So tension should be positive, weight should be negative. So our equation F net equals mv squared over r will be that net force T minus W equals mv squared over r. And then you can solve whatever you want from this equation. You see how different this one is from this one. This is at top. This one is when the thing is at the bottom of the circle. So again, circular motion problems, vertical circular motion, two types, two subtypes, object at the top of the circle, object at the bottom of the circle, they'll have different equations. And also object on top of a contact surface like a road or a bridge, it will have normal force instead of the weight, the string or tension in the string. So you can also have something like, for example, an object is going on a road that looks like this. You have a semicircular part of this road and you have a marble that rolls here, and you have to find the forces on the marble here. So in this case, again, you'll have weight acting downwards and normal force acting upwards, which will be the kind of tension force, right? So you should be able to write this net force equation for all of these cases. Okay, so we figured out that if we are looking for minimum speed, tension will be minimum, just 0 at the top. And then we can rearrange this equation for V. You can see that m's will cancel and V will be just g times r and square root. Next problem is this one. So we have radius of a website says that the radius of the orbit of the moon around the earth is increasing by small amount each year. However, the time period of the orbit remains constant. Now for this one, you have to understand the problem statement very carefully, because if you try to solve it using equations, you will not, you'll get confused. You can try it, but if you just try to understand the problem, then you can solve it very easily. So it says that the radius is getting bigger. However, the period remains constant. The period means the time that it takes for the moon to complete one rotation, right? Or one orbit. So if the radius is increasing, but the time period is constant, how should the speed of the moon change? Should it be constant? Should it be increasing? Now, of course, if the radius is getting bigger, the circle is bigger. And if it has to cover the circle in the same time, then the speed must increase, right? So it's either option B or D. We can eliminate C and A. Now, what about angular velocity of the moon? This is important. So for angular velocity, omega is also equal to 2 pi over time period. And you can, actually it's 2 pi f, but we know that f is 1 over t, so it's 2 pi over t. And if you rearrange it for time period, you get 2 pi divided by omega. So you can see how omega and time period are related. If time period is constant, as it says in the statement, time period remain constant, it means 2 pi is constant anyway, so it means omega must remain constant. So it is option B. Okay, next question. This is again a unit conversion problem. So if you understood how to convert units, you should stop the video, try this question by yourself. We have a roundabout. It takes 12 seconds for the roundabout to complete 2 rotations, and a child is standing on the platform 1.8 meters from the center of the roundabout. Calculate the speed of the child. So we go back to our equations. We know that speed, which is linear speed they are talking about, linear speed v equals r times omega, right? So it means if we just can find omega, then we just need to multiply it with r, which is 1.8 meters. We can find v. So v equals r omega. Remember, omega we need in radians per second. Omega is 2 revolutions per 12 seconds. And now we need to convert this into radians per second. So we need to multiply again by our conversion factor, and it will be 2 pi radians divided by how many revolutions do we have in 2 pi radians? We have 1 revolution. So the revolution will cancel with revolution, and you will get 2 times 2 pi, which is 4 pi divided by 12, or you can have pi over 3 radians and radians per seconds. So this is omega. Now we just need to multiply it with r, which is 1.8, and we will have our linear speed. So v equals r omega 1.8 times pi over 3 radians per second. And the final speed with correct units will be in meters per seconds. This next question is interesting and also very important. First of all, you have to add to the diagram to show 2 forces acting on the bob. So we know that bob will have a force of gravity acting on it, which is mg, and it will have tension force along the string acting upwards. The second part of this question is derive the following relation for the angular velocity omega of the bob. Now here you have to stop for a minute and think before you write anything, okay? It's really important to look at this relation and see where it must be coming from. So first thing you notice is that we see a square root here, right? So if you are thinking about anything like v equals r omega or something, you see you don't have any squares on omega here, so you will not get a square root in the end. So this is the first thing I want you to see. Now, if you go back here to our equations, you will see that we have mr omega square in this equation. Centripetal force equals mr omega square. So if we rearrange this equation for omega, for example, we will get omega equals fc divided by mr square root. So that's the square root we wanted, right? So if we try to follow that equation, we need to use centripetal force. Now, in which direction do you think is the centripetal force acting in this case? This is a conical pendulum, which means that the bob is going in this circle here at the base. I hope you can imagine this. So the circular motion is at the base. Where must be our centripetal force? Centripetal force must point towards the center of this circle. So centripetal force must be pointing in this direction. So, okay, we are getting close to our answer. Now, the next question is, what is centripetal force? We see that the only 2 forces are tension in the string and weight, which is straight down, right? So which of these 2 forces will provide the centripetal force? We can see that mg is pointing straight down. It has no component in the direction of centripetal force. So we can ignore mg for now, and we can say that this tension force, it has a component, which is this one, this component is in the direction of centripetal force. So this component of the tension force must be equal to centripetal force. The next question is, what is this component? What should we call this component? So if this is our angle, theta, then this component of the tension will be, because it's opposite to the angle, this will be t sine theta. So we can write that Fc is t sine theta. So, okay, another step in the right direction. Now, the next question is, how do we know what is this t? Because in this equation, you see we have no t, right? So for t, we can use another equation, which is this y component of the tension force. So we can say that this y component of the tension force, because it's pointing up, this must balance the weight mg. So we can say that t, and since this is angle theta, this is also angle theta. So this component is t cosine of theta. This must balance weight mg. And we can see that tension, if we rearrange this equation for tension, tension must be mg divided by cosine theta. So we can substitute this equation for tension here in this equation for centripetal force. And we can write that centripetal force must be mg sine theta. So sine theta is this one. And then t itself is mg divided by cosine theta. So we have mg sine theta over cosine theta. This is Fc. So we can write that Fc must be equal to mr omega square, which is the equation that I showed you. And Fc is mg sine theta divided by cosine theta. So mg sine theta divided by cosine theta equals mr omega square. So I just substituted Fc here, and this thing is here. Now it already looks something like our equation, the equation that we want to prove. We can cancel the m's. So we don't have m here. We have g, which is a good thing because we need g. And the problem is this sine theta and L here, right? So now at this point, you might be tempting to write this R as L, but this will not solve our problem because here we only need cosine theta. But in our equation, we have sine theta divided by cosine theta, right? So you need to be careful. Now, which R is this? This R is the radius of the circle in which the object is rotating, or it is going in circular motion, which means this is the radius we are talking about. This is R. So how can you find this R? This is the opposite side of this length L of the pendulum. So we can write that opposite side R is just equal to L, which is hypotenuse, times sine of theta, right? So if you replace R with L sine theta, then you solve all the problems. You can get L in the equation, and you can also cancel sine. So we'll have g sine theta divided by cosine theta equals, for R, I will write L sine theta and then omega square. So sine theta will cancel with sine theta. L will be divided on the other side in the denominator. And when we find omega, we have to take square root on both sides. So final equation will be g divided by L cosine theta and then square root. So you see, you have to think what your next step should be to solve this type of problem. If you just start playing around with equations, rearranging it for omega and theta, and you'll keep going in circles. But if you just pause for a minute, think what the equation looks like, where each component might be coming from, how can you get the square root, how can you get g in it? So this g is also a good hint that you need weight somehow, right? You need to compare, for example, here, if you didn't know how to solve for tension, just by looking at this equation, you can see that it has g in it. So you can see that somehow I need to replace t with g, which is this thing, tension cosine theta equals mg. So if you solve these questions with careful planning, you can always get these equations right. It's not that difficult, it's just basic algebra. Now the next part is that a clock requires the period of the pop to be 5 seconds, length is given, and angle is also given. Deduce whether this arrangement leads to the required time period. Now remember, we already have omega, so we can write the relation between omega and time period, which is 2 pi divided by time period, and time period is 2 pi divided by omega. So you can just substitute these numbers here for g, L, and theta. You will have some omega. You can substitute that omega here. And if time is 5 seconds, then you can say that, yes, this arrangement will lead to the required period. And I'll just tell you that it will. You should get time period of 5 seconds. You can try this problem and you should get time period as 5 seconds. Okay, finally, we have to prove that centripetal acceleration is v squared divided by r. We have to derive this equation by considering the velocity of the poi ball at these two positions A and B. Your answer should include a vector diagram. So the question is that something about the poi ball, but the basic idea is that we have something going in a circle, in clockwise circle with radius r, center O, with constant speed v, right? So now if we have to draw a vector diagram, remember, what should our vector diagram include? Which vectors are they talking about? So acceleration is change in velocity divided by time. Change in velocity is v final minus v initial divided by time. Our v final, because this is in clockwise direction, our v final will be the tangential velocity at point B, which is something like this. And our v initial was the velocity at point A. Again, it will be tangential velocity, and it will be this arrow straight pointing to the right. Now, if I have to include a vector diagram, you can see that I have to draw VF minus VI. So I'll start with VF, which is something like this. And then I subtract VI following head to tail rule. So I have to start from the head of the first vector, and I have to draw the second vector, which is minus VI. Negative of a vector is the same vector in the opposite direction. So this is my negative VI pointing left. And this vector right here is my change in V. Now, after this point, I will do some acrobatics, so some circus tricks. And if you are not paying attention, you will miss the trick. So it's very important that you listen closely and follow. Even if you can draw the same diagram, because this is so important to understand. If you don't understand this, you will not be able to drive it in exam. So what we have here, we have this radius r, and then this is also radius, and this is our arc length s, right? So remember from the definition of radians equals s divided by r, right? I can rearrange this equation for s, and I can write s equals r times theta. Now the trick is that if this angle is small, then this arc length, which is an arc, which is a curved path, it will almost be a straight line, right? So here almost it is straight. Therefore, I can say that this is not something like this. This is actually just a small triangle like this. And then I can compare this triangle to this triangle. This is the whole idea. This is V final, this is V initial. And this is just like the sides of this triangle, which has sides r, and this VF and VI are also equal in length because this is constant speed, right? So we can compare these two triangles. Now what I can do is that this ds, which just means differential arc length, is equal to r times d theta. Why d theta? Because r is a fixed length, r is not changing, so only theta is changing. Now I can write the same equation for this triangle. I can say that dv equals theta, v, which is r, just like one side of this triangle. In this triangle, the side is v times d theta. So what I'm doing, I'm comparing this red triangle with this one, and then I'm writing the equation that applies to red triangle. I'm just applying the same equation to my triangle, which is this equation. If you understood all of this, then the rest is very simple. I can replace this change in final minus change in initial, or just this change in velocity with differential change in velocity. So acceleration will be dv over t, and then I can write dv as v times d theta. So it will be v times d theta over t. And if you remember, this will be dt, because as it moves between these 2 points A and B, the time will be very small. What is this d theta over dt? Or you can also write, you don't have to write d, you can also work with this triangle, change in velocity equals velocity times change in theta. If that's, I think, delta v equals v times delta theta. You can also use this. So it will be v delta theta divided by delta t. And now maybe you can recognize what is this delta theta divided by delta t. This is our definition of omega, right? Omega is the change in angular displacement over time. So theta divided by time. So I can write A equals V, this V, and for change in theta divided by time, angular displacement over time, I can write omega. Now, once we have this equation, we can use that omega equals, since V equals R omega, omega equals V divided by R, and I substitute this omega here, and I will get A equals V, and for omega, I can write V over R, and A will be V squared divided by R. I hope this was clear. Remember, you just have to compare these two triangles. And the next part of this question is very simple. So again, you see, like I said, you have to use equation for time period and omega, definition of omega in every other question. We have to calculate acceleration of the ball. Radius is given, and it completes 1.3 revolutions per second. So first of all, we can write omega. It is 1.3 revolutions per second. We can convert from revolutions per second to radians per second. So each revolution is 2 pi radians divided by 1 revolution. So this will give you omega in radians per second. And then you have to find acceleration. So you see we have our acceleration equation, A equals V omega. What I can do, I can also eliminate this V instead of eliminating omega. So if I eliminate this V, I will get that A equals V equals R omega. So instead of writing V, I can write R omega, and then another omega, which is from this equation. So my final equation for A will be that it is R omega square, right? So R is given, and omega we just calculated in radians per second, this one. You can just write it here, 0.58 times omega. Remember this one, 1.3 times 2 pi, and that squared, okay? This will give you acceleration. And then there is some comment, but I will leave this question as homework. You can pause this video. Okay, maybe I'll just solve it. The ball, as the ball goes around the circle with constant speed, the size of the force on his hand changes. Discuss whether his comment is correct. The child comments that the force changes. So of course we discussed this. If this is a vertical circle, when the ball is at the top, the net force is tension pointing downwards and the weight also pointing downwards. So the net force will be F net will be T plus W. And when it is at the bottom of the circle, the net force equation will be tension upwards and weight downwards. But the net force should always be towards the center. So we will write tension first minus W. So you can see we have different equations for net force. It means that the net force will change, and you can just explain it in 2 or 3 sentences.